Yeah, that's much better.
Way better. We're
All right. Okay. Yeah. Hi, everybody. I'm Jason Williams from Bloomberg. Uh, I'm mainly based in the London office, and my team focus on performance in the Bloomberg ecosystem. Yeah, I'm here with Jose DePina, who introduced himself earlier. He is based at Igalia, and Igalia and Bloomberg have partnered for quite a while on web standards, and Igalia have really helped us on implementations as well. Right, so container timing. I appreciate some people might not have seen earlier presentations of this, so I'll probably be talking for about 20 minutes just to bring everyone up to speed, and then we can have a chat for the remaining half. Essentially, what is it? What are we trying to solve? And yeah, how are we doing it so far? So I started off with a picture. This is Mark Seaman from Speed Curve. This was at Performance Now last year. And yeah, in this slide, he's showing, I quite like this, is a time to first tweet. And essentially he's talking about like limitations of LCP and also a little bit element timing as well, and how it'd be nice for developers to have a more bespoke API so that they can choose parts of the application or website that's important to them. In this particular case, this will be, X or Twitter or whichever, saying, for us, it's important to know when the first tweet is painted. That's when we know like the most important thing of that page is as rendered. It's not very easy to do something like this today. We have element timing, which only supports a subset of individual elements. That's quite problematic for developers who build stuff in a sort of component style way. There's a lot of pattern libraries and I guess atomic design today. And so it's not very easy to track when a component as a whole is painted. So to give you an example, this example's from Andy Davis from SpeedCurve. This is like a typical cookie card component. We can use element timing today. You can track the image. We can track some text. And that sort of starts to become challenging when you have other things like maybe the ratings comes from a third party, or maybe the buy now button hasn't rendered. And that's actually quite important because you can't use this card until the buy now button is there. So from a user perspective, it's not ready. And we want to know when everything is painted initially so that we can say this component was painted at this time, it was ready for the user, and maybe we can track that or mark that in Grafana or whichever stats we're using. The Bloomberg terminal uses Chromium for its rendering layout, so we do actually use many metrics, LCP, INP, long frames. And this is a nice example I like to show a lot. We got LCP choosing the title on the top right. A user would come to a function like this, and this is showing like market data and market indices, and they would be scanning this list of indices and trying to get an overview of the market. They would probably be looking for outliers, but to them the table's not really useful until it's had its initial paint. So for us, as developers, we want to know, when has that table finished painting? When is all the data there? When have the cells been populated? And that's something we want to track because of course people using this, they will probably come to us and say, when if there's issues with this table rendering and if the slowness, that's something we want to know about. And similar to the cookie issue and the times first tweet, for us, the table is the most important part of this application, not the title on the top right. So can we fix this? Can we do something better? That's sort of what we looked into, well, from last year, really. We started thinking about, can we have container timing, maybe as well as element timing? Can we know when a container has been presented, has been painted, and the user can start using it in some way? Can we offer the developer more control over what we have now with element timing? And yeah, again, similar as I mentioned earlier, can we have an API that's suitable for component design where developers will have a separation of concerns? They might even have a component that's made by a different team and they're displaying that on their website, and maybe that they want to track that separately. Can we have a modern API that sort of allows that? So yeah, when you start doing something like this, the first question you ask is, how do you actually know when something has been painted? That's quite difficult to do. It's not too easy. We did look at various ways of doing this. We settled on a candidate model. So if you imagine LCP, you don't really know when the largest thing is painted. You just get a new event when something bigger has come in. So rather than trying to guess, we have an API that will give you events when there's new paints happening within that container. And then the developer has the choice to choose the latest performance entry, or they might want to choose a performance entry that's before that they may feel is more important, but this puts a lot more of that in the hands of the developer. We did try some other things. We looked into like how much of the viewport was taken up, or within a container, like how has over 50% of it been painted. We did try these, but picking arbitrary thresholds didn't work too well. So yeah, we focused on the top one, which was rather than trying to work out, has enough painted for us to say, yeah, it's finished painting, or at least there's enough painted for the user to say, this is ready. We just give events instead. All right, so we started off with a naive proof of concept. We found very quickly that, of course, this will just run forever as things are changing. So to give you an example, when you mark a container, this is with an attribute, I'll show you this in a minute. We call this a container root. And we started off by just setting element timing to everything inside. So these sort of green rectangles represent elements starting to be painted. And we sort of collect the element timing events that happen, and then we sort of bubble them up to the container. So someone who's listening on just that container would get the events as well. That gets you pretty far, actually. That gets you most of the way there. One thing we found in the field was that sometimes components often swap elements around. So later on an interaction, or if you imagine a carousel swapping an image, you element swap, and then that triggers a new element timing, and then further down the line, you're getting even more paint. So we didn't feel like that was useful because this is way after the component is painted, and it didn't feel like a good API to continue surfacing those. So we had a better idea. We looked into an algorithm for only updating on new areas. We felt that if a new area is painted, that is an initial paint, maybe the container is still populating itself. So same again, the user marks the container they're interested in. But this time what we do is when we come across a container root, internally we create there we go. We create a region. This is a skier region. I think Chrome calls it CC region. Don't worry too much about the code on the left, but essentially we just create a new empty region every time we hit a container. I believe every browser engine has something similar. I think Firefox also uses Skier, the 2D library, and I think WebKit does in some platforms. I think it also uses Core Graphics, which I think has a similar API, but I think most browsers should be able to
Firefox does not.
Does not use Skier?
We're still able to do this.
Okay, cool. Thanks. So yeah, we then start having elements that come in, and we essentially just add those to our region as they start having their initial paint. So similar to before. The advantage this time is that if those elements are removed or the component swaps them out, we do keep track of the areas that have been painted. So again, like a carousel or something like that, if we place a new image later on, it's a no-op, nothing happens. We don't emit new events after that. Only in new areas we count that as a new initial paint. So if we go back to the API, if you was using container timing, and you're getting your elements, populating your components, when we swap out, you wouldn't get a new container timing event at that point, only on fresh new paints. This should be much better for knowing when your component has had its first set of initial paints, rather than continuing paints happening through user interaction or swapping images or elements later on. So where are we today? Well, we have an explainer on the Bloomberg repo. We have a Chromium implementation thanks to Dape. And we also have a userland implementation as well. There's a JavaScript version of this. So you're free to play around with that. You're free to try some of these out. And there's also a Chrome extension, which does need the build. and that gives you a few more things as well. All right, so yeah, how you use it, pretty similar to before. You have an attribute which shows your, similar to element timing actually, you can just mark your attribute where you're interested. You can give it a name, just like element timing as well. You use the performance observer, but your entry type is container, and then you can do whatever you want with those entries. And you get something like this. I'm going to go into more detail on this on the next slide. So right now, this is still sort of up for discussion and still sketching out the API, but today, this is what it looks like. You would have an entry type of container. The start time would be the time of the latest paint that happened within that component or container. Similar to element timing, the identifier is, whatever you mark it as, or it can just be an empty string. The size is the combined region. So all of the recs inside of that container that's been painted so far, that should always be ever increasing. The intersection rect is the total bounding rect of all paints. The first render time is the first event really, the first time that container's had a paint. Duration is always 0 because this is more of a point in time sort of entry rather than a duration based one. And we added last painted element as well. We felt that this would be useful if developers wanted to know why a paint happened. So if we didn't have that last field, it might be tricky to know why. I saw there's entries coming through, but I'm not really sure what's triggering that. So this just sort of this lets you know which element came in last. That could also be a stream of elements. That could actually be an array of elements because there's obviously in each batch there's more than one thing painted. So, but for now it's just the last one.
What does last one in this context mean?
So in the latest batch of paints within that container. So
it's when you say a batch of paint, you just mean a single paint that contains a batch, a list of elements. Okay.
Yes, yeah. Yep. And that could be a list of elements in that. Right now we just choose one of the most
a random one that was painted in that paint.
Yeah. This is probably not going to be easy to see. But this is just a quick example on a very basic page. This is just a quick example that asynchronously loads some more content into these containers. There's two containers there. There's the outer one, and then you can't really see it very well on this, but the inner one is like a red border, and you can see that we just have some events coming through. Again, feel free to play with this week. You can actually load this and down. You can pull this on GitHub and just play around with it. But essentially, yeah, as you get some text coming through, you get more container timing events, and then eventually it will stop at some point when there's nothing else happening. But yeah, you can see the inner and outer on the identifier, and then you do get size and start time and various and so on. All right. Nested containers. We have had this question a couple of times. How do we deal with that? For now, we have 3 modes when you nest a container within another. We default to ignore. So in this example here, if you do have an inner, and then you've got a performance observer on both, it will ignore, the outer will ignore anything happening on the inner container. And it will just pretend it doesn't see it. So it will just stop traversing down once it hits another container, a container route. We have transparency, where the outer container would see everything happening inside in the container. So it would almost be as though that container timing didn't even have that route at all. It would just continue traversing, counting anything inside of there. And then we have shadowed, which is similar, but instead things like last painted elements and size would be based on the root of the inner. You wouldn't give any information away from the internal elements happening. We added this mode just in case we wanted to support sort of like shadow DOM or something further down the line. Maybe it could work something similar to this and work in this way, where you get information about the root but nothing inside. All right, so some questions to put to the floor. The first one is, well, I just showed you the nesting and the different nesting strategies you could do with this. Right now, it's quite difficult to do that with Performance Observer. with Performance Observer, you have your entry types, or a single type. You have a buffered flag, but if we want to add options per type, that's currently not something we can do. Actually, even in the polyfill and the implementation, we have to sort of add this in a different way. We would like to know if it's possible to have the option to add options on a per type basis. Could this be useful for other proposals? Maybe not, I don't know. But yeah, the question did come up whether we can do something here. As right now, it's not really too easy to set that. The second question we have is, how do we include other elements in this? More and more people are using SVGs for their logos on their websites, which don't get taken into account on element timing and therefore LCP. Is this something that we just add to element timing and then container timing will just work with that? Or is there something we can do there? But yeah, the question is, how do we support more and more of these elements that have internal nodes in them? I guess there's mathml and table as well and various other things. So that's another question for the floor as well. And then within performance, yeah, I guess this is kind of related to the per type options. Would we want to unobserve on interaction? So we imagine people would use container timing to know when the container's had its first paint. So once people are interacting with the page, similar to what I think Web Vitals does with LCP, do we care about continuing to have this run? Maybe we could free up resources once we know we don't need it anymore. And if that is the case, is that something we could actually do at a performance observer level? Because maybe that could be useful for other types as well. Maybe like LCP or layout shift. Maybe there's other types that might make use of this. So could we do that, or should this be left to user land level? And yeah, I think that's it. The final question at the bottom, which I didn't touch on, is, do we want to, are people interested in experimenting with this? Like, do we want to have an intent to experiment in this area? Is WebPerf working group interested in sort of taking this on and adopting this? Right now, it sort of lives in Bloomberg and with Igalia, but is this something that the Web Performance Working Group would be interested in looking at and taking on as well? Be great to have more help on this also. And yeah, that is it. Those are the questions that we would like to discuss and also hear from some browser vendors and people in the room. Yeah, that's the floor.
Wonderful. I'm gonna. Okay. Okay, so there's a few of us at Akamai that are interested in pushing forward some thoughts around the reporting API or error logging, or maybe something else, specifically around getting better insights into happy eyeball type behaviors. So on the call, there's Utkarsh. He works with me at Akamai, and I'm not sure if Eric Nygren has been able to join. He may or may not join later. We work, of course, in IETF related things, and Happy Eyeballs is one of the projects that's kind of going on there, and we want to make sure that we have the right visibility into it. So kind of some joint thoughts. So I'm actually going to hand it over to Utkarsh, if that's okay, and have him lead the charge.
Good. All right. Thanks, Nick. Hi, everyone. This is Utkarsh. So I'm going to get into some things that we think that could help if we were to add into the real user monitoring and other APIs that browsers support today. And it's all coming from the fact that in the last decade or so, we've all been working on new standards and implementing those standards. And the list is pretty long: V6, H3, H2, H3 over Quick, SVCB, and many things, right? And we have ISPs all around the world. They have different configurations. Some support some things, some don't. For example, V6 is supported somewhere, and in some places it is not. Some places it works better, some places it doesn't. There's still some routing misconfigurations. Sometimes it's broken. Same thing with Quick. Sometimes it works, sometimes it doesn't work. And then we have this concept of happy eyeballs, which is which is just trying to give preference to newer protocols so that we get away from the old ones, right? And DNS is part of the happy eyeballs. Some clients do quad A first and then go to A if the quad A fails or it's too slow. And this basically leads into giving preference to IPv6 compared to v4. Some happy eyeballs behaviors also support giving preference to quick connections versus H1 or H2, right? So the list is quite long. And next slide, please, Nick. Thank you. So just to give an example of happy eyeballs, how an example happy eyeball behavior might work for a client is initially it would like to start preferring an IPv6 connections, right? So obviously it would do a quad A lookup to get an IPv6 answer. It tries that and then it gets to a TCP handshake situation, and then a request response happens. But in parallel, because the clients do not know if the IPv6 connection is going to be successful, so what they do is some behaviors they delay an IPv4 lookup just in case the v6 fails. So there is a delay, and then an A lookup starts, and then an IPv4 TCP handshake starts. But in the meantime, the v6 has been successful. All good. Browsers cancel the IPv4 connection setup and they just use the v6 because it has already been successful. Now, this is a good condition, right? But there are situations where we start with a v6, we get an IPv6 answer, we try to connect, but it fails, or it just needs a lot more time before we classify it as a successful connection attempt. And so what happens in those scenarios is that IPv4 connection setup succeeds. And so browsers, they fall over to v4 connections, and IPv6 is just abandoned because it failed. Next slide, please. So the way current browser reporting works really is that it reports on absolute successes or failures. Did this happen and did it happen successfully? Yes, let's collect the reporting metrics around it and then let's report those to the backend servers. Same thing with failures. We tried this and it failed, and that's it. That's the end of it. And then let's report the failures. But the problem really over here is that there's a lot of things that are tried in the middle, and none of that is reported. And network error logging assumes there is a fixed ordering of events. A happens, then B happens, then C happens. But that is not really always the case. And just going back to the happy eyeballs example, some clients would even do parallel DNS lookups. They will seek for both quad A and A answers together. Some would do serially. Same thing with TCP connections, right? So there's things that are not classified as absolute successes or failures. We tried, they failed, but we had a fallback. And the fallback is what we are reporting. Quick versus TCP connections. Some connections may start with TCP handshake while they're waiting for quick to succeed. There are multiple DNS lookups that happen through browsers, and some DNS records, they guide the connection behavior. And the list is longer than this, honestly. Next slide, please, Nick. So just to give you an overview of what we see, what we are missing, really, the left side in the red pink bubble, we have the success, the DNS handshake times, the connections, TLS, request response models, all the 400 5x's. Then on the right side, we have the HTTP, all the good stuff, the successful connection attempts that gave us a 200 OK answer. But everything in the middle, we lack visibility today. The IPv6 fallback, the quick fallbacks, the DNS problems that resulted in all of these things. And these happens during the navigation part. There is another side of the story, which is the post-navigation. And today, what we're missing from the reporting is things like the TCP resets. And they could happen due to NAT rebinding protocols, or if during an H2 or H3 connection, if there's a stream reset or an upgrade request, then we miss information about those. Path MTU is another thing where some clients would send packets that are smaller than the MTU size, but then the later packets that go on after the connection, they're bigger. And so what that does is it breaks the IPv6 connections. And we lack visibility into those into those details today. And so we're not able to understand what the problem really is because there's always a fallback. And so if a fallback happens, we think everything is good, but there's so much more that we are unaware of today. Next slide, please, Nick. So in summary, what we really don't know is when do fallbacks happen? Is it because we tried a quad A lookup and it just simply timed out? Maybe because the quad A doesn't exist. IPv6 problems, we tried IPv6, but it timed out. Does it mean it's broken, misconfigured? Was IPv6 slower than IPv4? That's why there was a fallback to IPv4. I talked about the path MTU earlier, which is, did the IPv6 connections just break because the packet sizes were too big? Quick related problems, the quick connections could be timing out. Maybe some ISPs are dropping packets, but in the browser happy eyeball behavior, there would be a fallback to a non-quick protocol. Maybe ISPs are rate limiting packets, and this might be something tricky to identify using browser APIs. But this is something this is that information that we're still missing today. Next slide, please.
Takes a little while for the screen to catch up. I'll take over from here from Utkarsh for a moment. So we've Eric Nygren, who's also on the call, was able to file a few issues kind of covering some of the details. So this is NEL issue 175 and 176. So the first one is kind of more covering the happy eyeballs failure reporting and kind of how it relates to reporting API network error logging. You can obviously get into those issues for more details, but the crux of it is that there may be some success after there's been a fallback, right? If you tried IPv6, it didn't work, fall back to IPv4. Maybe that's slower than desired. Maybe just knowing the fact that this fallback happened can be useful for not only content delivery networks, but also potential us working with other ISPs to help solve some of the problems that are happening here. And it really just, can help reduce some of the unreliability of clients interacting with CDNs and ISPs. That's very hard to monitor today. And then the second issue is around, let's say we do have a successful connection, maybe even a successful navigation. Streams can get reset, things can get lost. The TCP stream might have to be restarted. That's rather invisible right now, but it can be indicative of other networking, CDN, ISP issues, whatever you want, and it could be useful to monitor. So wanted to start the discussion with the working group to see if there's any other entities that are interested in kind of understanding these things from a networking perspective a little bit better. Eric, I know that you're on the call. Is there anything else you wanted to add in particular about either of those two issues right now?
Not at the moment.
So yeah, we want to see if there are new insights we can gain. Waiting for the slide to catch up. Why did the fallback happen? Was it because it was too slow and it eventually succeeded, but we had moved on? Was it because it was broken? Was it because some ISP or some network was not able to satisfy what we were trying to ask of it? Which protocols were tried? How long potentially were those protocols tried for before falling back to something else? Was it timed out? Was it abandoned? And this can help potentially us understand, would it have eventually succeeded if we had given it more time? Maybe browsers could get a little bit more insight into the timeouts that they're doing. The clients can get some more insight to the timeouts that they're using for connection establishment. Basically, at the end of the day, was it a problem with the network? Was it a problem with the server? Was it a problem with the client? All three of them? Who knows? What we have today that's somewhat similar is network error logging as part of the reporting API. So you can register for either a failure fraction, basically the percentage of failed requests that you would like to be pinged about. Or you can register for a success fraction, which is the opposite, just getting notified of successful navigations or resources. An example success report is on the right-hand side. There is a lot of questions around, is this even possible to surface up? There's questions around the privacy implications. And then, of course, there's questions about, is something like network error logging even a good fit for this, or is there something else? Could we extend network error logging, for example, to have a few additional details about yes or no, I tried the quad A record and then fell back, or not, or something, a very naive example is on the right. Probably not what we are actually recommending, but just something to kind of give food for thought. Or do we do something entirely different specifically for happy eyeball like cases, right? IPv6 to IPv4 fallback, quick to TCP fallback, etc. So we can, build a more performant, reliable web. So that leads us to some of the questions that we have from this. Do we try to remodel? Okay, so there's a couple things around network error logging specifically. One is around network error logging's concepts of kind of the connection phase, where it's a rather simplified model, which was very nice for scoping it and implementation of there is a DNS, there is a TCP, there is a HTTP request. That is slightly different than reality in some cases, right? There may be parallel things happening. There may be multiple things happening. Would we try to, if we wanted to include some of this information, have to remodel some of those phasings of things? Or do we just try to, and then do we try to, fit some of this information into something like network error logging so that we can get better insight into it? Or do we just try to, fix the very specific use case of happy eyeballs and have some other reporting mechanism? The IETF, and Eric probably has more details on this, but the IETF has, or is considering starting a working group for happy eyeballs evolution. It probably would be good for us to coordinate, communicate, and just kind of be aware of what's going on there. And this is probably an initial discussion for that. But it would be good for us to kind of all be aware of what's going on. Anything, Utkarsh or Eric, that you would want to add?
Yeah, I think I would just add that the kind of a lot of the motivation for this came out of the conversations with the IETF, because as we've, like, every time happy eyeballs comes up, this is one of the primary concerns that gets raised is the degree to which it hides information about problems in the network or problems on servers, and highlighting the need to have ways to collect those. But because that's been a client-side issue of how do you collect that, that's been somewhat outside of the remit for the IETF, which is where the thought that network error logging would be a fairly obvious, or one obvious candidate for how we might be able to collect some of that information. And the happy eyeballs evolution work at IETF is being motivated out of it evolving beyond just the IPv4 to IPv6 fallback. IPv6 to IPv4 fallback to also cover additional use cases such as falling back or handling quick and service binding records and the like.
And I don't think we covered it specifically in this deck, Eric, but one of the things we had talked about before were like an example or two of some of the kind of deployment challenges and how that was negatively affecting users and origins. Would you mind sharing like one example of something that we've come across as a CDN?
Yeah, like as a CDN, we've seen in quite a few cases where actually two different directions. One of which is end user networks getting broken. Is if end user networks break IPv6 but keep IPv4 working, sometimes they don't notice for a while, and it becomes hard to chase down this, and it's causing performance problems for the users within those networks. And some clients are able to handle happy eyeballs fallbacks well, but not all clients have. So sometimes the inability to catch those problems results in content getting switched to IPv4 only in order to work better for some really old naive clients at the expense of more modern clients. That's one example. Another example is there are a number of large server operators who have all kind of broken IPv6 in a few common ways. So for example, breaking path MTU discovery is something that at least 3 of the largest server operators in the world have all done at various points in time. And being able to have some, and most of the time that gets hidden behind happy eyeballs falling back, hopefully, but having some better visibility on the server operator side would make it easier to be able to operationally respond to those sorts of issues.
Thank you guys both for adding to that. That's all we had as a presentation, so I'd probably like to switch it over to any thoughts or questions from the working group. I'm going to pause recording.
You've been doing some. Thank you. I've been doing some investigations into TTFB and found a world of pain that's made my life hell for the last couple of months. And it's not fair that I should be in pain without the rest of you. So I was looking for a group of web performance minded people, including RUM providers and browser implementers and all that, to discuss this with. So what better place than here? So I'm going to talk about TTFB today, an older metric, not one of the exciting new ones, but one that I think has some problems. So TTFB, I'm sure I'd be very surprised if anyone in the room has not heard of this. It's one of the oldest metrics, but also one of the most ill-defined, which is a little surprising. So first of all, we'll talk about what is time to first byte, or TTFB. We'll have a look at the spec for that. And there is no spec for TTFB. And I think it's one of the only things that we measure that there is no spec. Even DOM content loaded or onload or spec'd in the HTML living standard, but time to first byte isn't. Now it does build on resource timing, which is spec'd, but anyway. So if we look at MDN's definition, there's 2 kind of definitions whenever you look in the web that come up over and over again. One is MDN. They have what looks like a very clear definition. Time to first byte refers to the time between the browser requesting a page and when it receives the first byte of information from the server, includes blah, 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 and they even have a formula for it. So that seems quite clear, and there's nothing to talk about here, and I'm going to waste 45 minutes of your time talking about nothing. But formula seems obvious. That formula is from the performance timing API that none of us really use anymore because it's old and horrible, and not the newer performance navigation timing API. So the MDN definition is at the very least stale and could do with an update. And I was actually intending to go ahead and update that, but that's when I ran into my first problem, is I didn't know what to update it to. So the other definition, and I'm totally biased because I work on this site, is web.dev's definition. This one's a little difficult to see, but they have a very, caveat is that I helped write this. They have a very similar definition: the time between the request for a resource and the first byte of a response begins to arrive. And we use the resource timing API in this thing. And we say TTFB measures the elapsed time between start time and response start, which at least uses the new API. So yay for us on that. But we have a big paragraph below that page where I talk about other definitions of TTFB, alternative facts, if you will be, because we've broken TTFB recently. And that's what we're going to talk about in this presentation, is some of this sort of stuff here. So what is TTFB used for? It's used for lots of things. We can use it to measure server response time, to compare different hosting providers. We see people measuring that. It's a baseline metric which holds up all the other timings. So it's a very important one to measure because you can't measure your first paint or your LCP or anything else and without knowing your TTFB before that. It's one of the few cross-browser supported metrics, so yay for that. And it helps understand page load experience. It helps also understand redirect, DNS, or HTTPS issues. So great for all that. And what is TTFB good for? Well, the short answer is not one of those damn things that I mentioned earlier. Because it doesn't measure server response time, or at least not in a meaningful way that's understandable. And lots of people see a high TTFB and they assume it's server response time, but quite often it's redirects or something else. Comparing hosted providers, again, because it doesn't measure that, it's not a very good way of using that. It is a baseline metric, it is useful for that, but what it means is messy. It is a cross-browser supported metric, except that not all the browsers implement it in the same way, which means it's not a cross-browser supported metric in my mind. It's not good for understanding experience. So we in the Google Chrome team have spent a lot of time looking at core web vitals, and we try to look at things that actually users experience. Time to first byte isn't what a user experiences. It leads on to what a user experiences, but nobody really cares when they see the first byte into their browser. And then for a similar way that you can't understand server response time, you can't use it to understand DNS HTTPS issues. So all the things that people say it's useful for are lies. And the basic problem in my mind is that TTFB tries to cover too much. So going back to performance navigation timing, with lots of these little things, TTFB tries to cover all of this. And the endpoint is messy, and we'll come to that in a minute. And the problem with that is you can't really use it then to understand any individual parts of this. So subparts are to the answer. So I'm a big fan of breaking things down and subparts or components or various pieces. So you could redirect, or you could break it down into the redirect part, the service worker part, the HTTP cache part, and DNS, TCP, and HTTPS sort of connection setup part. And that will give you more information about what to do. And I actually tried to do this in the Web Vitals JS library and failed miserably because you can't really break it into the subparts. And some reasons of that. Redirects are kind of messy. There's been I think a 4-year-old issue that no one raised saying there's 2 redirect timings in there. We set them to null whenever they're cross origin, but you kind of just measure the next time. It kind of gives it sort of with some problems in there. Service worker, while doing this work, Phil Walton and I found a whole load of issues in browser, cross browser, and all this messiness where the timings just don't make sense and are all kind of messed up. The HTTP cache has no timings, so if we return to the diagram, you'll see some of them have got timings, some of them have got start timings, some of them have got end timings, some of them have got neither. HTTP cache doesn't have either, so you kind of are looking at the domain lookup start to try and guess that. And if there's no worker, you can kind of guess it. If there is, it gets really messy. And yeah, DNS, TCP, and HTTPS is kind of there. It gets kind of somewhat messy with HTTP, where the last two are kind of joined together. So yeah, it's a little bit messy of what you're getting there. And then Lucas brought up earlier, because browsers use happy eyeballs and connect, sometimes it's not on the connection. The DNS has already been done on another connection that isn't actually used here. So it's a little messy. And there's lots of what I'm calling lost time, making all of those kind of inaccurate and difficult to measure. Now, Tim Vareke from Akamai spent ages coming up with an acronym that was 3 letters and then very little time actually to explain it. No, I jest. So he's come up with this UNO, unattributed navigation overhead, which unlike TTFB follows the well-known guidelines of performance acronym being 3 letters, not a TTFB. And he's basically saying, look, there's lots of these bits where browsers are doing things or things aren't messy. Now, I'll be slightly cynical and say that Tim works for a CDN and he wants to explain why his CDN isn't slow. So he's happy to say it wasn't us, it was browser, and explain that the bits that they're in charge of is accounted for. But the point is, this shows that it's kind of messy. And although he's attributed some of the unattributed stuff here with this metric, there's lots of stuff in between here. There is no gaps being measured here, even though there definitely is gaps in there. Going back to performance navigation timing, we tried to put subparts in this, and I wanted redirect time, I wanted that, but couldn't really do that. So I've got these vague definitions of waiting duration, which is kind of mostly redirects and a little bit of browser time and who knows what. Cache duration, which is a bit of servers work, a bit of cache. So it gives you a little bit more information, but it's not great. And if you're using service workers, some of this is just messy. So TTFB is good for telling you when something's wrong, but not so good at telling you what is wrong, and resource timing and its various components aren't that great. So that's our first problem with TTFB, is we all use it, we all like it, but once it tells you something, it's very easy to misunderstand it. The second problem is, what does first byte measure? Like what first byte? And for this, I want to talk about early hints. So I was at my very first TPAC 2 years ago in Vancouver, and Colin from Shopify came along and talked about early hints. And one of the problems that we said is it kind of breaks TTFB. He raised an issue and someone else came along and said, yeah, TTFB is a broken metric at this point. So they've got able to measure TTFB, they implement early hints, and it all drops down to 0. And TTFB looks super fast, even though nothing's really changed in the traditional definition of TTFB. So a few clever people and one not so clever person, me, got together and we fixed it. So Noam suggested raising final response headers, start and end times. We should have listened to Noam, we didn't. What we ultimately implemented was first interim response start, which is when the early hint gets sent. And that meant that response start went back to being the old response start. So that graph would no longer be a problem. It would jump back up and everyone would be happy and all was good in the world and we were happy again. And we put it back to where it was. The problem was that this was effectively a breaking change, and any old browsers that don't, sorry, not old browsers, any browsers that don't support this are still sending the response start, including the early hint. And that includes, I mean, Chromium's the only one that has implemented it, so all other browsers don't implement this. And therefore, we've suddenly just broken, we get different results from different browsers. And we've created an interop issue with this. So did first interim response start solve breaking time to first byte? Not really. So any browser that supports early hints, and now all 3 browser engines, major browser engines do. There's a slight difference between whether they support pre-connect and preload, but ignore that for purposes of this conversation. Only one of the browsers supports first interim response start, and therefore only one of the browsers excludes early hints in TTFB, and the other 2 don't. So if you're using RUM and you're using web performance APIs, you're getting very different results for sites that use early hints, depending which browser you're getting it from. So RUM is different between Chromium and the other vendors, and it's not even implemented evenly across tools. So in case you think I'm using this podium to insult the other browsers, I'm not. Even within Chrome, we've done a poor job of this. So Crux, which is our public telemetry API, doesn't use first interim response. It was kind of implemented in our web API side of the house, but not in our telemetry API, which Chrome, the Chrome user experience report ultimately uses. So TTFB ends with early hints there, contradicting what you measure in RUM. So you're sitting measuring something in RUM, comparing it to Crux and getting different answers. Similarly, Lighthouse uses telemetry API. So now they don't call it TTFB, they call it server response time. But again, it ends with any early hints being heard. And I'm equally not trying to throw shade on the Chrome side, but I just wanted to show that changing ill-defined things is hard. And we implemented that a couple of years ago, and we haven't really done anything, we haven't really improved the situation since that. And similarly, most documentation doesn't mention neither first interim response start nor early hints. So the MDM example earlier. And those that do try to document it, like web.dev, has this huge paragraph that's horrible to read and confuses the whole situation probably more than it solves it. So no, I think, is the short answer. I don't think it did solve it, and I think if anything, it just broke it more by at least introducing a cross-browser compatibility issue and a cross-run, internal system issue. And then there's a bigger question of, is it only Early Hints that has this issue? So it's always fun when CEOs fight in public. So Toby from Shopify posted this from ismyhostfastyet.com, which unfortunately is owned by my team, but anyway, where Shopify looks great because they've got great TTFB. And they said, yeah, good, but we can do better. So wasn't quite boasting fully there, but he's saying, look at us, it's great. And Guillermo from Vercel came back and said, this is rubbish. That's only because you're using Early Hints. And I don't know how he figured out the Crux didn't report properly because it took me ages. But anyway, he either figured out or guessed it or whatever. He said, that's rubbish, you're using Early Hints. That's the only reason you're fast. And that doesn't really tell you anything. And it's not great. And stop using about this to boast about your hosting providers. Which on one side is a very fair point. And on another side, is totally ridiculous because Vercel and Next.js use early flushing. And why should we treat them differently? So Early Hints says you can send an early hint, a 103 response while the body's still being generated. For an early flush, you can flush the head while the body's still being generated. So you're sending some stuff before you know what the full page content is, or even if the page is going to be generated correctly. It's for both of them, it's the earliest time. I mean, the whole point of flushing early or sending early hints is to give extra work to the browser that they can get started on ahead of time. Both of them do that. The first, early hints, may not be used to send meaningful resources. You could just send a pre-connector to, like in many cases in the Shopify example. You're not sending much more work than that. You're not really gaining that much. Similar in early flush, you could just flush a title and that could be it. Now, maybe that will show in the browser tab and it's a little bit of feedback, but it's not really any meaningful work being given. There is some differences. One doesn't start to render the page. The other one does. As I said, it will put the white page up, maybe put the title in the tab. Early hints does allow, if the page fails, you to send a 503 or whatever back. Early flushing doesn't, so you have to do some other things. So there's some slight differences. But on the whole, they're both used to send early stuff. So I'm not entirely sure that it's right or fair to say one cheats TTFB and the other doesn't. But who am I to ask? And like before, I've done a lot of whinging here. In case it's not obvious from this, I do actually like time to first byte. I think it is a good metric for differentiating between front-end work. I think Steve Souders said that 90% of performance is in the front end, not in the back end. And everything else. And I'm deliberately not saying the front end or the back end here because, as I say, time to first byte, because it includes redirect, because it includes other things, doesn't necessarily mean just the back end. So that's all very interesting and somewhat depressing. But why am I presenting this to you? What's my ask of you? So my asks of you is, should we try to fix any of this? And if so, how? What do you all consider TTFB to be, or do you even care about TTFB? Do any of you use it? I'm guessing the RUM providers at least. Should we stop using the term TTFB? I tried to dig it up, but no one suggested time to first body or some other metric that I don't think we can even measure at the minute. I think personally it's so ingrained in everything that it's unlikely we're going to move on from this, but maybe that's what we should do and see. Is there any interest in Firefox and Safari in implementing first interim response headers to solve the interop issue at least? And before you answer that, let me see the final point that we'll get to in a minute. In future, I think one of the biggest takeaways from this is we need to do better implementing non-breaking changes. In hindsight, first response headers and bodies would have probably been better than first interim response headers. And I think it was me that suggested doing it the other way around, which what we ultimately implemented. The thinking behind that being all our graphs would go back and nobody would have to change anything. In hindsight, that was incorrect thinking. And yeah, now we have a situation where we still have to change everything and to recognize this new thing, and we haven't done a good enough job of that. And then also in future, I think we need to do better to consider more holistic solutions. So we were in a bit of a panic to solve early hints because it was being rolled out. But we never thought about a bigger solution that could be solved early hints and early flush together. Like if we had final response headers or final response body back, could that have been something that we also admitted for the early flush use case and therefore measured them both fairly? And then finally, before we ask Firefox and Safari to implement that, should we change our minds of what we did 2 years ago and put response back, start back to where it was, and implement final response headers and body? Or is it too late and nobody wants to revisit this and we're all tired and want to go home and cry ourselves to sleep and do something else? And that's pretty much all I had to say on that. So I'm looking forward to hearing what the rest of you think. And if you have any thoughts, or am I just making a big deal over nothing?
Yeah, so I'm somewhat relieved the room's not full of pitchforks, given the name of the title of the the talk, but it's part of why I stayed remote, you know. So yes, it's a dead horse. We've been over this and over this and over this for probably the better part of decades. Cache partitioning, common resources, should the browser ship libraries, sort of all of that rolled into, hey, why don't we look at it again? So one of the things that we did in the HTTP archive, I want to say maybe 2 months ago, I pulled data from this month's crawl, so September, was we added the SHA-256 hash of every response body that we pull, image, even things that we don't store. So images, fonts, every response that we have a response body for, we logged in the HTTP archive. So we can see what the duplication of resources looks like across the web, independent of URLs. So not just things served from the same origin, but your typical jQuery shipped by 10,000 different sites kind of thing. It turns out there were 17,000-ish that were seen. What I'm sort of qualifying as pervasive as seeing on more than 10,000 different top-level origins. 150 of them were seen on more than 1 million sites, which is sort of the extreme level of pervasive. So since it's the SHA hash of the entire body of the response, what it doesn't capture is bundled code. So React, things like jQuery included in your bundle of other code that's been minified and grouped together. Anything that's been edited or changed from, like if you removed a copyright, added a copyright, any change that was made to the original sort of breaks you out into a different file. And different versions of jQuery, for example, will show up as different resources, obviously, because they differ slightly. So the 150 number in the top million is 150 different iterations of a given file. The crawl spans maybe 5 days, I think, that it takes to run. So some of the things that are revved fairly frequently, we may have picked up a couple of versions of them, even if it's not something like jQuery. The slides are all in the agenda, so don't worry about writing things down and linked, just so you can get to any of the links. This is the actual query that was run. Please don't criticize my SQL, BigQuery SQL too much. I suck at SQL, but it worked. It probably ran for a week's worth of CPU time, so I don't really recommend running it unless you've got Google paying the bill for it. Down at the bottom is a CSV of the 17,000 resources and how many origins they showed up on that you can just access directly. There's basically 2 or 3 different types of resources that showed up. You've got the things that kind of rev fairly frequently, things that are third-party embeds, the YouTube desktop player, for example, the analytics, ads code, things like that, where it's a common URL used by a lot of sites. And since it's a URL controlled by the third party, they can release new versions of it whenever they want. Same thing goes for party things like Shopify, Wix, that kind of thing, where they control the platform. Even though it's a bunch of origins, they can rev the code kind of whenever they want. And then there's sort of the slower changing long tail of resources that are self-hosted by sites of libraries, CMSs, WordPress, that kind of thing, jQuery, where they tend to rev less frequently because it's whenever a new release gets pushed out or whenever a site happens to adopt the latest versions of it. The things that showed up, by far the most popular things that were common were scripts. Probably not a big surprise. I was a little surprised as many fonts showed up as they did, and not just Google fonts, like everyone's using the same 3 or whatever Google fonts. There's a lot of Font Awesome sites, it looks like, that are using self-hosted fonts that are, maybe it's a theme, maybe it's a common font in WordPress or something that they all use, but there were a fair number of binary fonts that were self-hosted that showed up on a large number of origins. And then you've got a sprinkle of CSS and a few images that are from common things like a WordPress template or a Wix template, something like that. By far, probably no surprise, the most popular one, Google Analytics. The well-known, at least the one version of it that showed up at the top, and I didn't look closely enough to see if maybe I picked up a few different versions, was on 14.5 million pages out of the, I want to say it's 50 million-ish that we tested. It's not too big. jQuery was, I think, the second or very close to the second. The interesting thing with jQuery, obviously, is the origins that it's served on changes wildly. And I think in this case, oh yeah, it wasn't specifically the WordPress, but WordPress by far drives the largest lion's share of jQuery, at least standalone file usage in the web. And it wasn't that far behind Google Analytics at 11 million origins, and the libraries for jQuery, jQuery UI, all that kind of stuff was a little less, but it still showed up on a lot of sites. reCAPTCHA, called that one out specifically because it's relatively large at 217K compressed. Showed up on 10 million pages, which was kind of a surprisingly large number of pages for reCAPTCHA to be on, at least for loading the library, even on a cold load of a page. YouTube, I think, was the largest one at close to 800K for the player and showed up on a few million sites as well. But it's not just sort of the big well-known libraries. A lot of Font Awesome, Google Maps, Facebook events, sort of the third-party embeds that you expect to see a lot. There was a whole lot of Shopify code and libraries that was embedded in sites. And then the third-party or the first-party self-hosted stuff, we saw a lot of WordPress. Boomerang was out there a lot. Wix, Yandex, Twitter, a lot of the common embeds that we're used to seeing for the last few decades. And so cache partitioning and how we got to sort of where we are. Yeah, and that's the beating a dead horse pitchforks meme, because this is where we start going. Most, if not all, of the browsers now have moved to a triple keyed cache for the data cache, the disk cache at least, for the resources. So there is no more sharing of downloaded resources across top level sites, at least. In Chrome, it's top level site plus the frame origin plus the resource URL are what make up the key. And so even within a given site, if you're loading the resource from 2 different iframes from different origins, you won't be sharing the same resource. And so there's a fair amount of duplication. And in the links at the end of the slides, I have a link to a GitHub, I want to say document that the Chrome team published about cache partitioning, where they talked about the triple key cache performance impact. It was anywhere from negligible to 1% on LCP, I want to say, and 3 to 5% on cache hit rate and resource loads. The thing to remember about a lot of the data that comes out from that kind of a report in UMA from Chrome is that it's usage-based. And so people who visit a lot of the same site fairly frequently aren't going to see much difference. It's whenever you happen to hit a new site or the one-time page load looking at a news story or whatever kind of thing that are sprinkled in a user's visiting patterns that don't show up in the 75th percentile of UMA data kind of thing. The unpartitioned cache risks, sort of the things that we try, the things that have killed every attempt to use a shared cache and maintain privacy for the most part. If you put unique data inside of the payload and make it cacheable, you can basically use it as a cookie, right? You put the user ID or whatever inside of the response, you generate a new one every time it hits the origin, but once it's in the user's cache, you can go ahead and use that as a cookie. The more insidious versions of that are the existence of the file at all. Say you have 32 unique files that you can put in cache, and for any individual user, you fetch a subset of those. You effectively have a 32-bit number that you can assign based on which resources you put into the user's cache. And so it's not even the contents of the resources, but just the existence of those well-known resources in a given user's cache. If you can successfully probe the cache non-destructively to see if resources are in there, those can be abused as a tracking vector as well. Leaking the history of sites or technologies that the user has been to. This is a particularly gnarly one because the sensitivity to it is not a site decision, it's a user decision more than anything. Sort of the canonical example is a map tile or a authentication provider, knowing that you have looked at a map tile for a sensitive location, for example, may target you by some governments, for example, or knowing that you have been to a certain bank's website makes you an easier phishing target because they can target you for that bank, for example. And that it may not, the site itself may decide, I don't care about the map tiles, it's not sensitive data, but as far as individual users, it could be. And unpartitioning the cache doesn't really solve the jQuery problem, where you're self-hosting the resource on a dozen different sites, for example. Even if you had a unpartitioned cache, unless you are using from a well-known CDN, and we've been over that for years, that just doesn't happen, and has connection overhead and all sorts of other things. So earlier this year, I was maybe innocently or unknowingly trying to tackle each one of those to see, can we get to a place where we can share some of these resources, just because the opportunity space feels like we're missing out on the ability to reuse things that are already in the cache. If we have the client use the integrity on attribute on a resource or on a fetch, we can eliminate the explicit tracking of the payload because the client already knows the payload, effectively knows the payload when it's making the request. And so there's no way to add additional data to the client that the client didn't already know. It doesn't solve any of the other problems, but it's one checkbox, and we can get rid of that first one. One of the things that we started looking at in the Chrome side of things is, can we identify resources that are well-known, that are public, that are static and unchanging, that we can whitelist, for example? And is there maybe a way to declaratively say these things are immutable and public? And so what if, and this is me just spitballing here, feel free to shoot it down later. So you need to know at the time of fetch if you're going to look in a shared cache or a partitioned cache if the resource is going to be public or private, and if it comes out of a public cache and if it's immutable or not. In HTTP, we have the cache control public and we have the immutable response headers, but we don't have anything until we get the response to know that. And so for now, let's assume there are new attributes that you can say that this will be a public resource, this will be immutable, and you have the integrity hash of the resource that you're trying to fetch. If you fetch it from a privacy protecting cache, for example, like the IP blinding proxy kind of infrastructure, that's a trusted cache, and the cache can tell you this resource was requested by a lot of different clients and I have it in my cache and it was served to you from my cache. Can we get to a point where we can then use that in a shared cache in a way that we know that it is pervasive, it's unmodified, and it's not targeting specific users? And we would add some logic where things that are marked as being immutable and public are not probable in the cache beyond anytime you try to read an item that is set that way, it is indestructibly written to the cache so that you have a one-time read, basically, effectively, of resources in the cache that qualify. It doesn't solve the problems. It makes them more probabilistic, where the first person who happens to try and sniff your history might be able to see where you've been, at which point they set your history as if you had been to use one of those technologies, but it doesn't completely eliminate the privacy concerns. So I'm not sure we can get there. It feels like we're close, but you're still leaking information about some level of history, right? Is this a new user browsing with an empty cache, or like if you're probing for a well-known resource like Google Analytics, for example, that's on almost every site, and you happen to land with a user that has a cache that doesn't have Google Analytics in it. Maybe they've never been to a site that uses Google Analytics, or maybe they don't have a cache that's populated. And so you're still leaking some information about the users. And it still doesn't solve the jQuery problem of sites serving the same copy of the same resource using different URLs. There have been some discussions and threads about using SRI integrity to address resources. That has its own security nightmare behind it, so we're not even going there. This discussion is all about resources served from a given origin, and is there a way for that origin to not be partitioned? And I see Nidhi's in the room and a lot of the other Chrome team. They can give you more background on the Chrome experiment that we tried with a manual list. The main problem with the manual list is by the time we actually launched the experiment, a lot of the resources had since versioned and the list was stale. And so it's a difficult problem to tackle manually without some form of automation. Which brings me to dictionaries, which is sort of a different take on resources. Is it, and at one level, is a pervasive dictionary something that is safer to share, perhaps, for a given origin, but it may still not solve the jQuery problem unless we look at a pre-installed dictionary. And so this is kind of where my current, I'd still like to solve the cache partitioned problem. I'm not sure it's solvable, but in the meantime, Broadly already ships with a small dictionary of common web terms in it. Would it be possible to ship with a larger dictionary and use the compression dictionary transport stuff that we just standardized through IETF, where we can negotiate between clients and origins the available dictionary that the client has for compression? And so it's basically like the Broadly built-in dictionary, but it can potentially be larger, and it can potentially be versioned and updated over the years. So we can have, say, the 2024 version of what we qualify as the web dictionary that has the current versions of React, jQuery, and other things that are commonly seen on the web. When we talked years ago about browsers shipping libraries, for example, which is kind of a similar space, the problems that had was there's no like one version of jQuery that everyone's using, right? And if we ship a version of a library, we're pinning people to stick towards that version of the library. Compression dictionaries have an interesting twist to them where even if we ship the current version of jQuery as a dictionary, we can ship one version of it, and most versions of jQuery should still compress very well against it. And the site isn't using what we ship, the site is still using what they actually send. We can just compress it more effectively. So as they roll out security fixes or whatever else, it's still on the sites to update and get the latest versions of the security fixes, and they will still compress very well with the one version of the given library that we happen to include in the compression dictionary. It still does deter updates and code changes a little bit in that they won't compress quite as well as if you're shipping exactly what's in the dictionary, but it does solve the sort of problem of self-hosting a given file either standalone or bundling resources within, like jQuery, within another file, because it will compress out the jQuery bits no matter where they occur, for example. There are little niddly details, like we will be favoring whatever resources end up in that version of the dictionary. So does React, for example, get a performance benefit for having been popular in 2024 that now all of a sudden new libraries have to overcome to be able to become more popular than what we shipped? And that's a trade-off, right, between pushing innovation on the web and performance for users and reducing bytes and things like that. For something like jQuery that's extremely pervasive and isn't getting dislodged anytime soon, where would we draw that line? And then there's legal issues to sort out if we did go down this path about what can be included in a dictionary. Are there copyright concerns with what we actually ship and things like that? So I have a whole bunch of links, but I mostly just wanted to open it up for discussions of, is there something here that feels like in either path where we might be able to get some traction, or have we been down this road enough and we don't want to touch it with a 10-foot pole kind of a space? And we can go right into discussion. I don't know if you wanted to stop the recording, Yoav, or...